Okay, so now we're going to look at solubility and precipitation. So this should add a little bit to our understanding of electrolytes and look at why some things form electrolytes and why some things don't. We can't store solid ions by themselves. So we can't store, say, a sodium ion by itself. Whoops, my bad. It just doesn't exist as Na plus by itself as a solid. That's not a thing. We can have sodium metal, but we can't have a sodium ion. The same thing is true for negative ions. We don't have chlorine ions by themselves. We can have chlorine bonded to another chlorine as a diatomic molecule, but we can't have just a chlorine ion, at least not solid. So we store these instead as neutral ionic compounds. We pair up that sodium with the chlorine, and then we get table salt, or NaCl. So when they aren't dissolved in water, these electrolytes are solid ionic compounds, like salt. They are called salts. Those ionic compounds are called salts because they all typically have sort of the same properties. And they're cations. Remember, those are positive, the silly cat drawing, bonded to negative anions to form neutral compounds. So a soluble ionic compound in water dissolves to produce electrolytes. If we have one that's soluble, it's going to dissolve to produce electrolytes. And then these new ions either can bond with other ions in the solution to form an insoluble compound, or they can stay dissolved and just continue to be electrolytes in that solution. The new insoluble compound would be called a precipitate. That's the solid that's formed when we put two salts in water and we get an insoluble compound out. The insoluble compound that forms from the chemical reaction between two soluble salts. So we've got a soluble salt here, a soluble salt here, and we would get an insoluble precipitate. The S there stands for solid. AQ is aqueous or in water. And I think that's all that you would need for these. These precipitation reactions are always going to be double replacement reactions where we have a pair. This would be like the square dancing reaction if you can think back. Now we've got a pair of ions plus another pair of ions yielding a pair of ions plus another pair of ions. So we're just switching the partners. A pairs with Y, B pairs with X, and you can see that there in the products. In the example here, we're going to pair silver with chlorine, and we're going to pair sodium with nitrate. And again, our insoluble compound here is silver chloride. That's the precipitate. How do I know which compounds are soluble? That's a great question. If the attraction between ions is greater than the attraction between the water and the ions, then the water can't pull hard enough to separate them. So again, if you think back to that picture where, say, we've got a chlorine ion surrounded by waters. I'll just draw a couple of these here and you'll get the idea. And it's surrounded by waters. And then we've got a silver ion over here that's surrounded by waters. And again, there'd be more of them there, but you get the idea. If this attraction between the silver and the chlorine is too strong for the waters to hold it dissolved, then we'll get a precipitate. We would get this AgCl. So really this has a lot to do, excuse me, I shouldn't have put the negative there. This has a lot to do with how reactive these ions are and how much they want a partner. For something like silver and chlorine, there's going to be a super strong pull there, and so we're going to get a precipitate. For something like nitrate, NO3, that almost always stays dissolved. It's very, very rare that that would partner up with someone to form a precipitate. Another way to think about this, if the ions of the ionic compound are more stable with each other than when they're hydrated by water molecules, more stable together than when they're surrounded by waters, then they won't dissolve or they will form a precipitate. Now, you don't have to memorize these. You don't necessarily even have to find the trend. I've given you a resource with your solubility chart here. So I'm going to get out of the spreadsheet here, the presentation here. On the back of your periodic table, you have a chart that looks like this. Your excuse me, your solubility chart is this in the bottom right. I hope you can see the cursor here. but it says these anions soluble with, insoluble with. So if we look at the first row there, NO3 or nitrate is soluble with almost everything. So almost every time nitrate is going to stay dissolved, no matter what it's paired with. It's insoluble with no common ions. If we look at acetate, the second row, that's soluble with almost everything, not soluble with silver. So if we have silver and acetate paired together, we would get a precipitate, or it wouldn't dissolve. As we go down through there, if we look at chlorine or chloride, soluble with most cations, insoluble with silver, lead 2, the mercury, and thallium. So if we paired it with those things, we would get a precipitate or it wouldn't dissolve. And you can mix and match all the way down through there. So some precipitation reactions. First thing we need to do here is finish the equation. So we've got calcium chloride pairing up with silver nitrate. And when we do that, we're going to have calcium ions. And remember, calcium is plus 2 because it's in the second column of the periodic table, plus 2 chlorine ions, each minus 1. Chlorine starts with 7 valence electrons. It gains 1, so it's going to be minus 1. Plus silver, which is always plus 1. Silver is kind of strange. Plus nitrate. So it's kind of helpful to think about these things splitting up before we think about pairing them up again. When we put this in water, all 4 of those things are going to be separated. Now we're going to put these with their new partners. So we're going to pair the calcium with the nitrate, and we're going to pair the silver with the chlorine. When we do that, we're going to get Ca plus 2 NO3 minus plus Ag and Cl. Okay, we've got to make sure that we write the formulas correctly, so there are quite a few steps here. We'll start with the easy one. Ag and Cl, we've got a plus and a minus, so that's just going to cancel out to silver chloride. Calcium nitrate's a little more difficult. Calcium's plus 2, nitrate's minus 1, so we need 2 nitrates. We need 2 -1 nitrates in order to balance out that calcium. It's helpful to me if you think about Lewis structures here. We would have NO3 getting one of those electrons and a second NO3 getting the other electron. Each nitrate can only get 1 extra. So we would end up with that as our equation. Then we would refer back to that table. Excuse me. We would refer back to that table to determine which of these are solids and which are aqueous. Okay, so if we do that, I'm going to leave the slideshow here and I'm going to keep these. Nitrate is soluble with everything, so that one is going to be aqueous. Chlorine is soluble with most, but insoluble with silver. So if we fill that in here, we would have calcium nitrate, that's aqueous, and silver chloride, which is solid. The other thing we do need to do here is balance this equation. We would have a 2 here and a 2 there. I forgot to do that first. But our solubility chart would tell us that our calcium nitrate is going to be aqueous and our silver chloride is going to be solid. And that's what we get here. The order that you put these in really does not matter. You'll notice that when I wrote it, I have these two switched around. The order does not matter. It's just that the products are correct that matters. I want you to try a few more of these. I'll do the first one for you, and then I'll have you finish the last several just for some practice. And I will give you the answers at the end of the video. I'll have you pause it and work on them. So the first one here, we've got potassium iodide mixed with lead nitrate. Okay, we're going to do a double replacement. So we're going to pair our iodine with our lead, and we're going to pair our nitrate with our potassium. And we're going to get KNO3. Potassium's +1, nitrate's -1, so those come out nicely. Plus lead, which is +2, iodide, which is -1. So we're going to need 2 iodines. So our products would be KNO3 plus PbI2. In order to check solubility, now we're going to go back to that chart, and I'll escape out of here again. We would look at our polyatomics and multivalence. KNO3, well, nitrate's soluble with everything, and you'll find that that's a trend. Nitrate's used a lot to make sure that we have something that's still soluble here. And iodine is insoluble with lead. If you go to that, is insoluble with lead. So we would get a precipitate here. We'd have KNO3, which is aqueous, and we'd have lead iodide, which is solid. There will be some of these that you do where you don't get a precipitate, and that's okay. You would just put no precipitate or no PPT, precipitate, is produced as a result of this. And that's okay, it's totally normal. There are some things that we mix and they don't form precipitates. In this case, there is a precipitate, and it would be lead to iodide. I'll put the other 4 up here. I'd like you to pause the video as I'm doing this and work on these 4. I will come back and give you the answers in just a minute or two. Okay, so here are your answers for these. You can see the solids are listed here. All of your equations are balanced, except for the first one. I think I screwed that one up. We should have a 2 here and a 2 there. But your answers are there. Everything here actually had a precipitate. There will be some on your homework that do not, I'm pretty sure. But this should set you up pretty nicely to do homework 6.4.